when you're trained in some analytic methodology, you go into a problem with the language of your methodology, and you start
Yes.
asking questions that fit your way of solving problems. Those people are death. You've got to go in without any sense of methodology. If you can learn how to go in and ask the right questions, that's a great skill.
Hello, and welcome to another edition of the Decision Intelligence Lab podcast. Today, my co-host Mike Watson and I are joined by not one guest, but actually two. Warren Powell, who's a professor emeritus at Princeton University and a prolific researcher and writer, most recently the author of Sequential Decision Analysis in 2022 and Reinforcement Learning and Stochastic Optimization. Um, his work has helped me to kind of unify a number of different things I've learned about in bits and pieces: dynamic programming, reinforcement learning, and stochastic optimization. And he's currently working on a project about framing decision problems that kind of pulls together academic experience and industry collaboration. One of his industry collaborators is our other guest today, Adam DeJans Jr., who's most recently been working as a technical account manager at Gurobi Optimization, but was formerly a principal working on supply chain challenges at Toyota. And Adam has a deep love of mixed integer and linear programs, heuristics, and putting those kinds of technical tools to work in solving real problems. Speaking of real problems, he's also the co-author of a terrific book that's called You Got Your Data Job, Now What? And Adam, by the way, I feel like it should be said, the title should have been Dude, You Got Your Data Job. Or Dudette, You Got Your Data Job.
We thought about that word at one point.
And Adam, I just want to shout out two other things about Adam. He's really kind of a pioneer in trying to democratize optimization, to bring optimization to people other than PhDs in OR. And the other piece that's remarkable to me is he's a Detroit native, and he's somebody who came to math later in life and has kind of developed this passion for leveraging OR kind of the organic way, and then with a real focus on creating business value. So huge welcome to Adam and Warren. And Mike, let me turn it over to you.
All right, I'm just going to start off with a hot question right off the get-go. You guys are both prolific on LinkedIn. For people who don't know you two, are you guys friends or enemies, just based on your back and forth?
I retired early. I think 65 is an early retirement, and started building up my LinkedIn profiles. And then, Adam, you picked up, what, about a year ago? Something
Probably
like
a
that?
year ago, yeah.
And it really came across as like, oh my God, this guy thinks the way I do.
Yeah, I saw him post. For the record, yes, we're friends, not enemies. I've had this question come up recently. Say like, oh, you guys look like you're disagreeing. Like, no, just nuanced things. But yeah, I saw one of Warren's posts maybe like a year ago, probably more than that now. The time is going by quick, but I remember seeing something like, you can never actually solve a problem correctly, and like everything all these problems that you solve are done sequentially, and there's uncertainty that needs to be factored in. And I'm like, I was going through those pains exactly when I was at Toyota, in the largest supply chain in the world, essentially by footprint. So I really connected with him. I bought his book. I was reading the book. I'm like, oh yeah, this is making sense.
What are you guys trying to do on what are you guys trying to do on LinkedIn? Are you what's the reason you're so prolific? What's your ultimate goal there?
Well, there's a lot to cover under this topic. It's really quite astonishing how much the larger community, especially the academic community, has utterly missed, because virtually any decision has to be made repeatedly over time. Okay, there's exceptions, but the vast majority is just sequential. And once you say sequential, academics don't really use that phrase. They call it dynamic programming or stochastic programming or optimal control or any one of a bunch of other fancy names, each with very fancy math. I come from actually an engineering background, and as much as I do like math, I'm a problem solver, and I like working from a real problem. Adam comes from industry, and his career he's always solving a real problem. Whereas when you interact with the academic community, the most famous of them are really mostly all theoreticians, and they're coming from the math down.
Actually, Warren, that's perfect. What you just said sort of tees up the first question I was going to ask you directly. I think I own the title of least technical OR PhD extant. And so I'd like you to explain it to me like I'm a sixth grader in a non-technical way. How do you describe sequential decision optimization conceptually in the
Well, so
simplest
first
terms
of
you
all,
can.
anytime you want to control a problem, you got to make decisions. So
Okay.
the book I just sent to a publisher has no math. It simply asks 3 questions. What are the metrics? What types of decisions are you making? What are your uncertainties? So decisions are how you control the problem. So I love this line that I use over and over and over again. If you want to run a better X, anything, supply chain, health system, energy system, anything, you have to make better decisions. And most people nod and go, okay, yeah, I get that. But then you have to say, okay, well, what's next after that? I have to identify the decisions. I then have to figure out how do I measure how well I'm doing. So sometimes metrics are obvious and sometimes they're not. Sometimes decisions are obvious, sometimes they're not. And then I always like to slip in that after you make the decision, random stuff happens, and all I'm doing is describing life. I think this is one of the reasons why Adam connected, because I was pretty much describing what he constantly encounters. I mean, sorry, all I'm doing is just describing what actually happens.
So it sounds like there was sort of a gap in the way the academics looked at decisions and decisions over time. Can you kind of give us a description of the gap and the error and the thing that the piece that you're trying to fill with your work on SDO?
Well, so uh, when you think of the academics, almost anything we do mathematically dates to the 1950s. Sorry, World War II was the big, we got out of World War II, and all of a sudden, all this work in applied math just exploded. I mean, some of it predates World War II, but mostly it's post-World War II, which, by the way, we didn't really exactly have computers back then. And so there was a lot of heavy emphasis on the math. So Bellman comes up with this thing called dynamic programming, and he's proving theorems his entire life. And the theorems all got their own momentum, so there's endless people doing math, but you couldn't compute any of it. Danzig was back there solving his deterministic problems. Even he realized that uncertainty was important. He invented this thing called stochastic programming. It built its own momentum. It's an almost useless method. The engineers invented optimal control dating back to the 1700s, but it was deterministic. They didn't really put the stochastics in until the 1950s. Once you get this intermingling of decisions and information, things get really ugly. Okay, it's just, I mean, the most fundamental way of looking at decisions on 30 is think of a decision tree where you say, okay, I can make any one of a bunch of decisions, and then you have a bunch of random outcomes, and then you have more decisions. It explodes with astonishing speed. And that's what people run into. So Bellman looked like he had solved something, but he hadn't. And so what we got was this great momentum because academics, the way we advance things is we write a paper, send it out, and then referees have to look at it, which means other academics, which are mostly the theoreticians. And we really didn't have any serious numerical work happening till roughly the 1990s. By that time, the field had really settled its way in. So deterministic optimization really did quite well. Statistics and machine learning has been a fabulous field. It's done great. We have great tools. But that intermingling of decisions and uncertainty just never got off the ground. And my career started early 1980s where I landed in this thing called the trucking industry, truckload trucking. And you had to assign drivers to load, that's a decision. And then you had to wait for the loads to be called in, and that's new information. And I just went, oh my God, what a great problem. And I don't know how to write it down. I don't know how to think about it. And it took me about roughly 20 years to start, close to 20 years, before I started realizing, well, if you could do some sort of approximation of the downstream impact of a decision, that gets you sequences of smaller problems. That led me into approximate dynamic programming. Advanced another couple of, 10 or 15 years, I was working on a wide range of problems, and I suddenly realized that I was using a whole bunch of techniques. And it wasn't just approximate dynamic programming. And I realized this technique, this problem is just like Google Maps. When you try to drive to a destination, Google Maps is planning paths into the future, and you've got buy low health. I found I was using all these different methods that were just natural for the problem. And then between 2010 and 2020 is when I says, I can put all of those into these 4 classes of policies.
So actually, Warren, I'm laughing, smiling, let's say, because you've worked on this for more than 20 years. And Adam, when I talked to you, you said, "Yeah, Warren stuff, it kind of just formalizes common sense."
And
Adam, what did
I think it's a
Adam, what did
great
you
way to
mean by
describe it.
that? Yeah, I
I
think
think
it
that
is too, but I want to hear Adam tell us what he meant because he doesn't have the fancy degrees that we do, and he's not stuck in our academic paradigms. And the fact that it made sense to him was something I was really curious about. Adam, what do you mean it just formalizes common sense?
Yeah, so if you think about it, the whole premise of this is that the way I look at it is you can talk about states and all the actions and the four classes of policies, but you go to talk to business and nobody cares about that. But like, but like what like that's all formal, and I get you need to have it, and yeah, there's proof that this stuff works. Whatever, nobody really cares. Like when you go into business, they like common sense things to them are yeah, things are unpredictable. Yeah, that makes sense. Like, how do we add uncertainty into our decision making framework? Also, half the people don't want to use things like a Gurobi, for an example, or any MILP or solver. They don't know what that is. They might not trust it. And so you can start off with like very simple things. Like I like Warren's example of the order up to policy, and then there's ways to learn, well, what, like, at what threshold do we decide we need to reorder, and how much do we reorder up to, and these are things that are easily explainable to business. Even getting buy-in just from like, you're not going to use the same terminology at all. If you do, project is canceled. but like, it's really just laying out the fact that yes, we make decisions again and again. Like when you do inventory planning, every month you might do some type of order, or when you're in manufacturing, you're building cars every day. But and uncertainty comes in, of course, like parts are bad when they arrive, or parts show up late. And how do you handle this? So it's almost like it feels very natural to do and to explain. And of course, implementation is a different story. But I think that that's what I mean by it's like a formalized common sense in that aspect.
Like Adam, on your Toyota stuff, like how did you incorporate uncertainty into the models that you built? Like how did you think
Yeah.
about it? How'd you build that in? How'd you convince people to use it and that you were right?
So there's many types of uncertainty that you could imagine in the Toyota
Yeah.
supply chain. So some of our biggest ones are there's very catastrophic things that happen which are hard to account for. Like port strikes, for an example. There's a lot of unions at the ports, and like, how do you deal with that? Well, there's a decision that needs to be made of like, do we like, or some supplier can't ship something for a long period of time because of tariffs. Like, do you ahead of time decide to do some planning to keep spares somewhere? But then you have your more day-to-day type of things, like, oh, parts coming to a factory can be late. The actual staff showing up can be late. Um, People hurt themselves. Like, you have these, like, throughout the day things happen, and the easiest thing to, I mean, one way to convince people is to simulate what's actually going on, because then they can kind of see the results that happen. So a lot of these companies, they all have a policy, whether they know it or not. It's the default status quo policy. And like at the yards at Toyota, for example, it's not going to stop running just because somebody didn't formalize math on paper. Like, it's still going to run. It always has run, and there's not a lot of formality there, but there's some type of decisions being made, and you have to go and see the people, talk to them, see what is their default operating mode, and then you can take that, you come up with some heuristic to kind of figure out what they're doing, and then you can implement that in a simulation. Like, that's one way to do it. And now you can compare, okay, if I were to do some other type of policy, like, how does that compare? That's a really easy way to convince people.
One of these slides that I use in my talks is I had two ladders. And
Okay.
one ladder is our model of the problem, how we think about the problem. And one ladder is the sophistication of the policy. And usually it's best to start at the bottom rung on both sides to say, what's the simplest version of this problem uh, that I can represent? And then what's the policy that makes most sense for that? If you take something like an inventory problem, simple ordering strategies work best. But then as you start thinking more about your problem and you start thinking about the fact that there might be a strike, or there might be a change in design, or there might be something new with tariffs or whatnot, and you start making the model more interesting, then you have to start making your policies a little bit more sophisticated. You need to start climbing. So always you want to start simple and work up. I like starting with whatever the company's already doing. I think that's a good starting point in solving a problem. It says, what are you doing now? Because if you can just start there and formalize that and make it better, then that's a big win.
Especially
Yeah,
if you can find a pain point that just had, like, I remember about a year ago or something. I don't remember how long ago. Like, there was a port strike that happened, and like the tariffs is another really big one that happened. I got put on the tariff assignment. Like things like that allow you this gateway opportunity to come in with some type of new innovation, like applying some of this SDA work inside of it, because it was fresh, it just happened, they're still feeling the pain. Here's a solution. Like the thing that people get stuck up on is you have to be able to iterate quickly though. You can't say, "Oh yeah, I'll have this done in a year." Like that's not going to gain any trust or funding, as you know. So it's a balance. That's why starting simple is always the best.
well, so it does. There's something there. I really like the notion of the two ladders, but it also something implicit in that that I thought I heard. I want to kind of get verification from you guys. Is that along the way you're also sort of educating and being educated about the problem, and that as you kind of increase the sophistication of your understanding of the problem, if you've earned some trust along the way, you can then get to a more sophisticated solution that is demonstrably better. Um, can either of you talk about kind of experiences where you've had the business user and the people accountable for the results have some light bulbs go off around, hey, the problem is bigger than what we've been solving, and thus we're open to kind of more sophisticated solutions?
Yeah, I mean, I've made a career out of this, I would say. So like one example is the easiest example, and one of the most impactful examples ever is just supply demand. So like you have a limited amount of supply, there's some demand that needs to go out. In the Toyota type of case, it could be in like it was engines, batteries, transmissions. There's all these like raw material. Then there's like base demand for base type of cars, like a Highlander, a Camry, whatever. You don't know all the specs on it, but at a high level, you need to do this planning of like how much are you going to buy in what month and where are you going to ship it to and how many of those are you going to build. And you have factory constraints, you have supply constraints, you have a demand constraint. It's a soft constraint. But they were doing this, a lot of companies, and this team particularly was doing this manually, like with an Excel solver. Somebody said, "Oh, I think I learned something in school. We could do some type of like use some solver or something. It sounds familiar." And like I saw him doing this, I was like, "Yeah, there's a much better way to do it." And I actually used a Gurobi license. We had Gurobi license, and we used it for this. And it was just a very very simple linear program. Not even just a straight linear program. Had fractional vehicles and rounded it. And just from the automation aspect, like they gained a lot of respect, and they started to trust it. Oh yeah, if we can like even just automating this save them so many weeks of time, not to mention how much money in vehicles that were produced because we were reducing waste, and also not only reducing waste, generating more vehicles, which is more profit, so newfound profit. But then I took this and okay, well, hey, actually, I know you're struggling with tariffs, which is part of the supply. Well, we could actually make this a little bit of a more robust process, and then I built that up to handle tariffs, and then oh well, like what if there's uncertainty in the factories, and so I kept expanding it over and over. So yeah, trust is the number one thing. I've seen many cases where, especially when I was at Ford, I've seen a team of just some of the best talent in the industry, I would say, on one group, on one project, and they could not get stakeholder buy-in, could not do change management, and that project was done within 3 months. Everybody was like, "Oh, they're gonna build the greatest thing ever," and like they couldn't push it anywhere because everything was so technical and it had to be perfect. And you need to just be able to settle for something that works at first, gain trust, and then build up from there. It's the only way.
Climbing the ladders.
Yep,
Now, one of the
climbing the
things that
ladders.
so George Danzig was very proud of the fact that he says linear programming doesn't just solve a problem, it helps you think about a problem. And I like that, although I would argue that an LP is a fairly limited type of technology. The one thing that I liked about an LP was that it told you you need to identify your decisions X, you need to have an objective function, you need to have constraints. I love that about deterministic math programming because when you went over to stochastic optimization, when you go out to what I call the jungle of stochastic optimization, they don't have that. They don't have that. Well, you need to have the X, you need to have the objective, you need to have the constraints. When you go and insert uncertainty, you lose that. So my sequential decision analytics framework says, okay, I like the idea of having that specific framework. I just need something richer. So I need something with 5 elements. The state variable is what you know. It's information. The decisions, which are made by a policy. So you need to articulate the decisions, and then somewhere you need to design a rule for making decisions that will be designed later. Number 3, what is the sources of information that will come to the system? I call it exogenous information. That's all the uncertain stuff. Number 4, we need a transition function that tells me how to get from t to t plus 1. And number 5 is your metrics. Now that covers everything. Now, before you do anything fancy, now, by the way, I haven't told you how to make a decision. This framework, it's like the IP, which says, I'm not going to tell you what algorithm to use. I just want, you got to give me X, you got to give me the objective, you got to give me the constraints. My version of that doesn't have 3 things, I have 5, fine. But I haven't yet told you how to make a decision. Just like with X, you formulate the problem, model first, and then come up with an algorithm, then solve. I like the model first, then solve, but for me, solving means designing a policy, okay? The deterministic people think solving means coming up with a decision. In my world, no, what you need is to come up with the method for making a decision.
They also think modeling means a model that gets fed into a solver directly. I think that's a big disconnect.
What I really enjoy is that before we get to the computer, before we write a line of code, we want to think through the model in plain English, because this is the part where, you have to answer questions like, well, I love my big 3, metrics, decisions, and uncertainties, because take one of Adam's complex problems, simply sitting at a sheet of paper or a nice whiteboard and saying, here are my metrics, here are the decisions. The metrics on a complex problem, they're not easy, but they're not that hard. The decisions are much harder, because you go to a Toyota or one of these complex problems that Adam works on, it's not just one decision. There's all kinds of decisions. You know what? Before you do anything fancy, just write it down in English. And then the uncertainties, same thing. And please never use that word stochastic. Oh, the academics love the word stochastic. Just talk about the information that comes in, but it's not going to be just one thing. It's not just going to be one random thing. Toyota, Adam, I bet you could sit at a whiteboard and come up with a whole list of stuff that happens. I have other words I could use, but I'm being recorded.
Hey, actually, I want to riff on that a little bit. Adam, how did you get Warren involved at Toyota? And Warren, what were the benefits to you of that involvement? And Adam, what were the benefits to Toyota?
Well, I could tell you what got me down, because, by the way, I did pay my own way. Adam and I started exchanging LinkedIn messages back and forth, because I could see from what he was posting, I'm like, oh my God, this guy gets it. I like to think if I could take somebody who has no PhD training, no formal training, I will have a much easier time with that person than I don't mind deterministic optimization, but if they have any training in stochastic optimization, it's like I'm lost. It's like they get their brain locked into a certain way of thinking. But Adam, coming from industry, he realized that my language I was thinking is just the language of what's happening. Somebody at some point is going to say, Warren, do you realize what you're saying is just sort of obvious?
And that was Adam. He's the one who said that,
me.
Right?
Now, the 4 classes of policies was not obvious, but the sequential decision analytic, all I'm doing is writing down what actually happens. There's nothing fancy there. And so, but that's the starting point. But the key thing is you have to stay away from making the decision, model first, then sit down and say, how do I make a decision? Whereas that's not how academia works. Academia works where everybody's got their favorite hammer. And Adam and I started exchanging back and forth, and I'm sitting there going, my God, this guy actually gets it. He deeply understands this notion of a policy.
I am, as you're saying that, Warren, I'm deeply remembering this lovely book called Lucky Jim. And at the end of the book, where somebody gets hired for an academic role, the person that hires him says, it's not so much you have the qualifications, but you lack the disqualifications.
That's a great line.
And in
I
some
like
sense, what you're saying is that Adam wasn't stuck in the stochastic optimization box or the deterministic optimization box. He was free of those disqualifications that kind of walled off his thinking. That's a really interesting insight, because he just got it holistically and in English. Hey, I want you to say a little bit more, Warren, about state transition. It was one of your 5 notions, and that was when I was thinking about it. It's the state transition is a combination of the impact of our previous decision and new information that's received up until the time of the next decision.
That's right. Look, there's this function from optimal control. I'm going to give total credit to the optimal control people because they all use this concept of a transition function. It's very simple. They like to use the little letter F. I don't, but they do. Okay, fine. And then all it does is say, tell me the state of the system. Now tell me the decision you made. Now tell me that random stuff. I call it exogenous information. And the transition simply says, now here's the updated state. Now, let me tell you something funny. It's amazingly difficult to find a definition of a state variable. And I have a whole web page, tinyurl.com/on state variables.
Warren, you're freaking me out now because I don't want to get caught in a holy war between you and Marty Putterman. I don't want to be there.
Yeah, Marty and I are not on the same page.
I know.
And in fact, Marty makes a mistake in his book, page 97, where he talks about a traveler trying to get from A to B, but it's not just a shortest path problem. He puts in a little twist, and he utterly swings and misses it. Marty is one of those classically trained people who do not know what a state variable is. But I use the example of my colleague Erhan Schindler, who's one of the great names in stochastic processes. Erhan doesn't know what a state variable is. And I asked him, Erhan, what's your definition of a state variable? And he just looked at me and he says, that's what cannot be defined. So after we had a number of conversations, he was writing a brand new book and he comes down to me. He's all excited. He's around 70 years old at this point. This was maybe a decade ago. And he says, okay, Warren, I've got this all figured out. This is all on my webpage, tinyurl.com/on state variables. I have an entire description of what the theoreticians think. I then put down my version of it. But the Sutton and Bartow of reinforcement learning, the Schindlers, the Puttermans, Bellman himself does not know what a state variable is. What they do is they have an idea of what they need it to be for their algorithms, and then they come up with examples. So the newest book, I start off to discuss state variables. I say, hey, let's take 3 little problems. One's tic-tac-toe, one is a shortest path problem, and one is a very, very simple inventory problem. And each one of those, the very vanilla version, has a very, very simple state variable. And that's what they do. They say, state variable, here's an example. So I give these 3 trivial examples. And then I go through the 3 examples all over again, but I tweak them just a little bit. And it's amazing how easy it is to go from a really simple little state variable to something that's enormously complicated. State variable is just information. So you go to Toyota, and Toyota, you bring up whatever their god-awful screens with, I don't know how many gargantuan volumes of data. That's the state variable. State variables in real problems it's like the whole database.
So let me bring it back to something both of you said. I'm just trying to summarize something and see if I've got it right. Like, I think, Warren, you had the 5 things, like decisions, uncertainty, and you had the 5 lists. And Adam, you snuck in a comment saying like, basically, I think I read it like the linear program is not the model, but the model is like the whole concept. So I think what you guys are both arguing is that we should consider all 5 of those different things, decisions, the metrics, the uncertainties. So think about that whole thing and don't think about just one simple model. I may use a mixed integer program, but if I want to consider all those things and I want to bake that into an overall policy where the actual optimization run is one piece of this whole decision. Is that a right way to think about it, or am I missing a step?
Let me give an example with linear programming. Let me take one of Adam's problems, but in operational setting, you're not going to solve that LP once. You're going to solve it over and over again.
Right.
Let's say it's one of his allocation problems. So that LP at time t, let me now index everything by t. So you have the A matrix, you have the B vector, you have the cost vector. So A sub t, B sub t, C sub t. That's your state variable. Okay. Now make your decision is X. You have to sit down and figure out what your decisions are. But let's say that Adam comes up with this vector X. Now you have the decision. Fine, you make the decision. Now between t and t plus 1, new information coming in. A is changing, B is changing, C is changing. Then you have to solve the LP all over again. So how the A, B, and C are changing, that's your transition function. Now, the objective function is not the objective function for the LP. The objective function is you take those decisions from every point in time, implement them, and then evaluate how well they do over time. That's the objective function. And that's a big mind shift for people who come from a traditional deterministic.
But let me be more succinct in his answer. Basically, what you said Michael's, yes, that's correct. You basically you're taking one. It's almost like you're doing one layer on top of that. Where you're actually optimizing for the type of way you're solving it as well.
What do you mean by that? What do you mean by optimizing by the type of way you're solving? What's that mean?
So like you could try linear program. You could try Bob's rule, just some guy in the yard. Like you could try all these different things, and
Gotcha.
each one of these might require, like they will require some tuning exercise because you're gonna
Mhm.
apply this thing over time. So you can simulate over time to tune this, or you can do it in the field online. So you could deploy something. It's very expensive to do this. Deploy something, make sure you get the feedback in. Okay, adjust. It's almost like this reinforcement learning type of activity.
That's perfect, because I think what you're saying there too is like it's to start simple, and we have to be flexible, and like let's try Bob's policy. He
Yeah,
has a policy, like
yeah,
let's try it, and then let's
it's
let's
fair
adjust
game.
another one and see how
Yeah,
that works. I like it. Yeah, yeah.
and
Now,
Bob is pretty damn good, is
And
what
he
you'll
knows a
find
lot. He
out.
has a lot of he has a lot of constraints in his head when he came up with that policy. It wasn't
Yeah.
random.
But
Well,
I
and
am
the
going
other
to claim
piece,
that Bob's policy still falls in my one of 4 classes of policy. So whatever it is that he's doing. Well, one
For sure.
challenge when you have Bob is trying to articulate how he actually does make the
Yes.
decision, because just because a human does it doesn't mean it's simple.
Oh,
You know what I
on the
mean?
contrary, I feel like the challenge for a lot of human decision makers who have both a deep intuition built up from lots of experience, plus a kind of lightning fast interpretation of new information coming in, they're obviously very often not able to articulate why it is they do what they do.
So
Uh,
when I started my work with truckload trucking, you had drivers and loads, and you had to assign drivers to loads. Well, the optimization people go, that's an assignment problem. It's great. Now, go sit with a dispatcher and ask, how does he actually do it? And the answer is, he doesn't know. I don't know. I've spent dozens and dozens and dozens of hours with dispatchers. Every now and then, it's very easy. They take a driver, find the best load type of thing, where best is a topic for a different conversation. But every now and then, things would get complicated, and he would say, Warren, give me a few minutes. I got to work through this. And then he would just do something that I don't think he could replicate. And every now and then, there are some problems where you're like, look, I actually do know how to do this with math. And I'm sorry, we're just going to have to live with that because I can't figure out how that damn human is doing this.
Yeah, I look at I can immediately relate, Warren. In this office where I'm sitting right now, every year I've got to assign students to consulting project teams for my class. I have a list of preferences from them. I know the clients, I know the needs of the project, I know the skill sets of the students, all of which is hell to write down, some of which is easy, but collectively, and I never leave the room. I come in with nothing but Diet Coke and potato chips, and I don't leave the room until I've created a successful, feasible assignment that I believe satisfies all the hard and soft constraints. And my metric is how much complaining I get from either the clients or the students. Yeah, I can't put that into an LP.
Yeah, it's tough. So right now, my company, my startup company that my son runs, thank God he's running it. Oh my God. So decades and decades of my work in truckload trucking is now finally making its way to the field. And I will say, A, things are going well, but B, it's a slog. Okay. We've got companies that are just fabulous and they use the system and whatnot. And we have companies where it's just an uphill battle of getting people, because we give them a lot of flexibility. When we assign drivers to loads, we don't just say, hey, assign this driver to this one load. We give them a ranked list. And yet, even with that flexibility, uh, it's not just the closest load. It's the same type of issues, Vijay, that you're running into with your students. It's multidimensional, it's complicated, you've got personalities. Optimal Dynamics has put together a dashboard. Not only do we know in aggregate how well they're doing, we actually see what every individual dispatcher is doing. And we'll go in and go, okay, somebody's got to sit with Bob. He doesn't seem to be on the program now. And the human process dimension of dispatching drivers to loads, it's significant. And I sit there on Slack. Of course, I may have built the core engines, but right now I am largely irrelevant to the day-to-day running. But I will sit on Slack and look at the chatter on every single one of the customer channels, and oh my gosh, it's a challenge.
But I think we were right, guys, when the four of us said before we started the recording that we could talk about this stuff all day. Clearly, all of us have a certain amount of passion and curiosity about it. But to wrap up, I want to throw a question out to both Adam and Warren. And Mike, I want you to chime in on this as well from your experience. And that is, what can we do and how do we go about democratizing optimization so that it's not just PhD eggheads like the three of us, that there are more Adam DeJans emerging year in and year out? Uh, Adam, since we called you out by name, we'll let you answer first.
Sure. And to be fair, I do have a master's in mathematics, so
Yeah,
I don't know that I'm
no,
I'm the ideal candidate.
no, but in some ways, Adam, we missed this question because we had so much other interesting stuff to talk
Yeah.
about. The next time we have you on, we want to hear about your journey, and you were late to the party, but you have come bearing gifts to the
Yeah,
party.
that's an interesting one. So around democratizing, I think that we live in a very interesting time right now with the LLMs. So I will say one thing, like the LLMs they're not going to replace a solver in the sense that it's going to actually do the solve itself. That's not how it's trained. That's not how it's operated to work. But what it does do is it can do things like when you talk about Gurobi in particular, or any MILP solver, it's now getting to a point where it's formulating pretty well, and it's able to create formulations for simple to medium problems quite well, and people who used to not have access because they didn't know how to model can now start modeling things and ship it off to a solver. And then not only that, the LLM can help them interpret the solver as well. So if there's infeasibility, it can read that, okay, why is it infeasible, and it puts it in this natural language. To go even one step further than this, I think now you're starting to see the use of agents as well. And now you can see things like a solver agent, if you will, where you can type in natural language. It gives you the model. That model gets automatically fed to a solver and then automatically retrieved and put out in natural language. Of course, right now it's not good enough to do this with really crazy problems, but the people who really need it, like those planners we were talking about, like they're now going to be able to access this. There's a lot of data scientists who know nothing about the mathematics of even what they do in data science. They import scikit-learn half the time. They don't really know what they're doing, but it works and they get results. So we're starting to see this trend emerge, and I think it's going to be uh, a big difference where it's no longer PhD gate kept anymore.
So
Excellent.
my answer to that question, I used to, in fact, I still use this PowerPoint slide where on one side I have pictures of all different physical problems, and on the other side I have a guy hacking away at the computer, and in between I have a math guy modeling it. And my vision was we have to go from problem to model to computer. About a year ago, I've been interacting with Rutgers supply chain management department. Now they invited me in to interact. They warned me, says, look, Warren, these students are not analytical. But as I've worked on complex problems, let me take like a Toyota as a good example. When you have these complex problems, that that initial diagram of going from problem to math to model does not work. And you talk about democratizing. I now have a new graphic where I have 4 squares. One square is the raw, let's call it the business problem. Okay. The raw business problem stated in raw business English. Okay. Because any business problem is not going to start with anything stated formally. It's going to be just real people out in the real world stating their problem in the normal way. Now, I may want to get to the model, but in between, I created a new quadrant that I think possibly could be filled by the students in the supply chain management department. No math, no programming, but knowing how to ask the right questions. And it starts with metrics, decisions, and uncertainties. Now, if you want to model a game of chess, that's easy. Metric, I want to win the game. Decisions, the moves of the chessboard. The uncertainty, my opponent. I'm done. Now try to answer those exact same questions for, say, I don't know, Toyota. I claim that's not easy. It's not easy answering those 3 questions. You're not just trying to make the most money. Metrics are way more complicated at a company like Toyota or an energy system or a health system. My daughter's in public health. The decisions is what's really hard because if you want to run a better anything, you have to make better decisions. What's the decision? It's not obvious. So I was at a workshop at Amazon many years ago, and I was just getting into this decision way of thinking. And I said, so I was giving a talk on this, and I went to Amazon. I ordered a bunch of little red books, the ones that you can just take notes in. Any of you can apply this. Any of you can look around and say, I want to do better at something, anything. What are the decisions? It's not obvious. I don't think a ChatGPT can solve that. This has to be a human knowing the right questions. And so this is something, no math, no computers, but if you don't if you don't have somebody in there, especially people without the technical training skills, because here's what happens when you have technical training. I've seen it happen over and over and over again. Uh, the big math programming types can be as guilty of this as anybody, but so can the Marty Puttermans or anybody else. When you're trained in some analytic methodology, you go into a problem with the language of your methodology, and you start asking questions that fit your way of solving problems. Those people are death. You've got to go in without any sense of methodology. I call it my model first, and so you can't even go in with the framework. I would really like to have people who don't know what a linear program is. They don't know what any of these 4 classes of policies, but they do have this sense, because decision. So one of my recent posts was on what is a decision. I've got a new web page on what is a decision. So, okay, it's anything you control. That's my simple one, but that's too easy. You've got to be able to go in and say, what are all the knobs? What are the things that you control? This is a skill. I claim it's a teachable skill, but I think we should teach it. It needs tons of case studies. Okay. I bet I could take any Harvard Business School case study and simply add what are the metrics, what are the decisions, what are the uncertainties, and it would become a more interesting case study. Furthermore, you'd be learning something that's transferable to other problems. I've never figured out what somebody learns from a Harvard Business School case study other than how to solve one particular problem.
I'm teaching one tonight, Warren.
If you can learn how to go in and ask the right questions, that's a great skill. And let's say I'm a modeler, if somebody would come to me with sheets of paper saying, here are the metrics, I like to organize them in a pyramid, here are the decisions, and here's what they do, and then here are the uncertainties, I'm going to have a much better model. Because if you have, say, a deterministic IP guy going in, and one famous one that we were discussing before we started turning the cameras on, I won't mention him by name, he goes in and the only thing he wants to know about is stuff that fits his deterministic IP. And I said, well, what about uncertainties? He says, oh, well, that's too complicated. I'd have to do stochastic programming. So the thing is, you've got to list those uncertainties. You've got to ask the right questions without regard to what tool you're going to use. So I'm going to claim that's the first step in democratizing this.
So my 2 cents on that would be,
that was fascinating.
Yeah, no, these are good answers. I would add, like, my background is coming from, I saw the whole machine learning thing take off and optimization was left behind. And I worked really hard then to sort of make sure optimization was in the toolkit. Now with LLMs, the same thing. So my approach is kind of at the executive level to say, hey, there's LLMs, they're doing this. And then here's a space for machine learning, and here's a space for optimization. All these things are tools that you can use to solve. So I'm kind of approaching it and thinking of it like from that point of view.
But as long as optimization doesn't mean an IP, an optimization means anything that makes a good decision.
Yes, and so it's right. It's a collection of tools, right? It doesn't mean a particular technology, but it's also like the thing I'm trying to combat is like, yes, there is this, at the executive level, they hear a lot about LLMs and how great they're going to be and how great agents are. And I think to Adam's point, it's like, yes, these things can help break down the barriers to use in some of this other technology, but this other technology is still good. It's like it still exists. Like your supply chain team needs this kind of technology to solve these kind of problems.
Let me make 2 quick statements. First of all, an LLM cannot make a decision. It can mimic it. It can't make it. You need an objective function. LLMs don't have it. Number 2, Optimal Dynamics, I'm sure, is not the only company out there that has discovered that LLMs are really useful on pre-processing and post-processing.
And shout out to Harley Davis, who was a guest early in the podcast, who's been working on exactly this. Good call, Warren. People have identified the pre and post capabilities, and I still think there's quite a bit of work to do to get kind of to natural language on both sides.
Yes. Whatever we talk about with tools, they're still on the computer, and we need help talking to the computer, both the inbound side and the outbound side. And I think LLMs are going to fit that role very nicely, be a powerful tool.
Okay. Well, it's been a great joy to have both Warren and Adam on the Decision Intelligence Lab podcast today. And if you check the show notes, there'll be links to writings, books, blog posts. These guys are spending a lot of time sharing their perspectives and their knowledge with us, not just on this podcast, but also, and not just on LinkedIn, but also through a whole bunch of other things. Guys, thanks for all that you do for the profession and for the people that are out there trying to solve hard problems. And thanks to all of our listeners for sitting through what is our longest episode in our first 4-person adventure. It's been a ton of fun to have both of you guys on.
Yeah, thanks, Adam. Thanks, Warren.
Thank you.
Thanks for hosting this. I always love things that get to a larger audience. I think we're going to slowly but surely be getting out there. So I think just bringing sequential decisions, notice I stay away from all the fancy academic terms. I think we're going to realize these are everywhere. And we just have to get it out and make sure that people understand that decisions on uncertainty isn't necessarily, some nightmare mathematically. Every human, by the way, knows how to do it. We've been making decisions under uncertainty since we were, 2 years old?
Yeah.
Right. And it'd be fun, I think, in season 2, perhaps, to have one or both of you guys back on and talk about things like value function approximations. But we have filled both our calendar and our listeners' and viewers' heads today pretty darn well. Thanks to everybody. This has been really fun.
Yeah. Thanks,
Thank
everyone.
you.
Thanks, Vijay and Mike.